thermal conductivity comparator. So we are going to look at these three as far as steady state methods are concerned for thermal conductivity measurement. Then we have transient approach also for thermal conductivity measurement. And here we are going to talk about the laser flash method. So the general approach is we obtain a one-dimensional temperature field within the medium, okay, whose thermal conductivity we want to measure. We create a one-dimensional temperature field by appropriately, taking steps so that the heat is only confined to one direction. Then if you know the temperature field, so we can measure the temperature gradient. Okay. We also measure the heat flux, and knowing the heat flux and the temperature gradient, we can estimate thermal conductivity. So typically the heat flux is known because that is something you are supplying to the system. And the temperature field is obtained using some temperature probes like thermocouple or other temperature measuring devices. So this is given because you are putting into the system. This you are measuring using some instrument. And this you are estimating measurement of temperature gradient. And knowing heat flux and temperature gradient, you can estimate thermal conductivity using what is called Fourier law of heat conduction. So as it says, thermal conductivity can be measured either in steady state or using transient method. And these classifications are basically based on the temperature field that is created within the sample, whether it is a steady state temperature field or a transient field that is created. The steady state methods are known as calorimetric methods. And here you have to ensure that whatever heat flux is coming, it is utilized in creating temperature gradient. That means you are neglecting any heat loss. But in the transient method, the heat loss is naturally neglected because the measurement time is too short for any heat loss to happen. Okay. So in steady state, the one-dimensional temperature field is typically established, as we said,
Recording
equation.
in progress.
So this equation I'm going to show when we are going to talk about the transient method. So in the steady state method, when you assume that the heat conduction is one-dimensional and the temperature variation across the sample is linear, these are good assumptions that typically are valid in heat transfer application. If you have proper arrangements, so you can really confine heat to flow only in one direction. And typically, if you do not have a heat source or sink or there is no material defect, the temperature variation across the sample in case of a 1D heat transfer is typically linear. So thermal conductivity by Fourier law of heat conduction is basically minus the heat flux divided by the temperature gradient. Heat flux Q is given by the heat transfer, total heat transfer rate divided by the cross-sectional area divided by the temperature gradient dt by dx. So this K can be approximated as Q by A divided by this dt by dx can be written as delta T over this small delta. Small delta signifies the size of the sample, okay, the width or thickness of the sample. So basically this gradient is approximated as the temperature difference divided by a length scale. Okay. So this is the theory basically. So now let us look at the guarded hot plate apparatus. So this is a method for thermal conductivity measurement in solid materials which are available in the form of a slab. So this sample that you see here is basically the solid specimen in the form of a slab whose thermal conductivity you want to measure. And what you see here is the cross section of a setup. Okay. So you have the sample which are located here. Okay. And on the sides, you have insulation. Okay. This middle layer that you see here is the main heater. Okay. So you supply specific amount of heat flux. You do resistive heating or whatever means you supply some amount of heat here. The side, so this is basically from the top view, it looks like this. Okay. So this inner square is basically the main heater. And the outer ring is basically the guard heater. Okay. And there is about 2 millimeter gap between the two. Okay. And these points, the dots that you see, this is where you are actually measuring temperature. So these are thermocouple junctions. Okay. So from the cross-sectional view, so this is the main heater, and these two basically part of this ring, if you take a cross-section like this, so it is going to look like this, right? So these are basically the guard heaters. So here, and then the sides are insulated. Okay. So basically the heat from the main heater is not allowed to move to the side because the guard heater temperature and the main heater temperature is matched, right? And there is insulation also in the sides. So heat cannot flow in the sideways direction. So the only way heat can flow is in this direction. So that way you ensure that heat flow through the sample is one-dimensional. So this heat, where does it go? It ultimately is carried away by this water. So the cold water is coming in here and cold water is, hot water is going out. Okay, similarly here cold water is in and hot water is out. So this heat basically, because of this water running through the system, the heater is here and sideways the heat transfer cannot take place through the sample. The heat is basically one-dimensional. Okay, so this is the arrangement that you do to ensure that the heat flow through the sample is one-dimensional. And because of these guard heaters, so this method is known as guard hot plate apparatus. So basically, you restrict the heat flow in the lateral direction and only heat flows through the sample in the vertical direction. Okay. So why this is necessary? So you have the heat flow through the sample. So you know the temperature at different points on these the main heater. So that means you know the temperature distribution. And you can also measure the temperature of the water, okay, by putting thermocouple. So if you know the temperature of the heater, if you know the temperature of water, you basically know the temperature gradient across the sample, okay? And you know how much heat is you're supplying to the heater for heating purpose. If you know the current, you know the resistance, you know I square R, basically the rate at which you are supplying heat. So you know basically in this equation, you know the total amount of heat, you know the area because you know the geometry of the plate, and you know the temperature gradient. So you can evaluate thermal conductivity of this sample. Okay. So this is the guarded hot plate apparatus. This is the second apparatus, which is known as another guarded hot plate method. Here, the here, this is basically used for solid sample. Okay, this arrangement is used for solid sample. But if you use liquid sample, one problem that happens in case of liquids or even gases is that when you apply a temperature gradient, there is convection that takes place. Okay, because of the natural convection, whenever there is a temperature gradient, the fluid will start to move. Okay, that doesn't happen in case of solid, but in case of liquid or gas, the moment you have a temperature gradient, they start moving. So when they start moving, and they start moving because of the gravitational effect, the phenomenon is known as natural convection. So this movement of the fluid will bring in inaccuracy in the measurement. Okay. So there are two ways to address this issue. One way is that you make sure that the fluid layer, whose thermal conductivity that you are trying to measure, is very, very small. Okay, the thickness is so small that the Grasov number, which is a non-dimensional number that characterizes, how strong is the convection or the movement of the fluid, is very small. That means the movement of the fluid has negligible effect on the heat transfer characteristics, and the regime will be mainly conduction dominant. Okay, this is something you can ensure. In addition, you can also ensure that you use some kind of configuration where the hot part is above the cold part. Okay. See, if the hot part is below the cold part, then the temperature gradient is going to be in the upward direction, and the movement is going to be very strong. But when the hot part is above the cold part, that means the density is lower in the upper part than the lower part of the fluid or the gas. It is called a stable configuration. See, we know that hot air rises up, right? So if the density is low down, then it will rise up. But if the density is low up, it has nowhere to rise. Okay, already heavier air is down, so it is basically a stable configuration. Okay, so this is also something that you can ensure. So these two are ensured by this arrangement that you see here. So essentially here you have again a cross section of the setup that you see. This thin layer that you see, thin white layer, is basically where you introduce your liquid sample or fluid sample whose thermal conductivity you want to measure. Okay. And there is cold water in and hot water out that happens. And this heater that you see here, this heater is the main heater. And this heater that you see here is the GAD heater. Okay, and there is a gap between the two, like the previous case, right? There is a 2 millimeter gap between the two. So here there is a similar gap. Now, the purpose of the GAD heater is that the temperature of it is same as that of the main heater. That means the heat flow is from the main heater is prevented from the upward direction, because there is no temperature gradient, there won't be any heat flow. Okay, so that means the heat is only allowed to flow downward. Okay, heat is only allowed to flow downward through this liquid element. Okay, so that means you have achieved the objective that the liquid layer is thin. That means the convection will be negligible. You have also achieved the one-dimensional heat flow that you need to equate with the heat flux and find thermal conductivity. You have also achieved the objective that the heated side is up, not down. Okay, so in the liquid layer, the density will change from the offside direction because the hotter side is up. So that way, the liquid would not really move that much. So it is in a stable configuration, right? So you have achieved all the objectives using this setup. And by measuring the temperature of the heater, by measuring the temperature of the water, you can actually get the temperature gradient across the liquid layer. And by knowing the temperature gradient, by knowing how much of the heat flux that is supplied to the main heater, you can find out the thermal conductivity. Right. So this is the hot plate apparatus for liquid. We talked about hot plate apparatus for solid. Next, we look at a radial heat conduction apparatus. Okay. So it is just geometry-wise different. Principle-wise, it is still the same. So basically, you have this is again a section of the setup, and this is a cylindrical setup. So you have an axis. The axis of symmetry is given by this dotted line. So you can see that the heater is basically a concentric heater. Okay, this is a cylindrical heater, and here you have a heated plug. So this is some kind of material that you put in, which avoids direct contact between the heater and the liquid layer. So now the heat is only going through radially outward because these ends are basically insulated. Okay, the ends are insulated. The heat is allowed to only go in the radial direction. And so you have basically sample liquid comes in and goes all around this concentric, the ring type of fluidic space, and goes out there. The water goes in here and comes out there. The water, the purpose is it basically enables heat transfer. And this heat transfer through this liquid layer, whose thermal conductivity you want to measure, is only radial in nature, and it is one-dimensional. One-dimensional and only in the radial direction. So instead of using the Cartesian coordinate system of writing down the Fourier law of heat conduction, you basically use a radial direction. So here it will be K will be equal to minus Q dt over dr. Okay. So the principle remains the same. You measure the temperature of the heater, you measure the temperature of the water, and you measure the temperature gradient. And knowing the heat flux applied to the heater, you find out the thermal conductivity. The third kind of apparatus that is used for measurement of thermal conductivity is known as thermal conductivity comparator. Okay, so this is a relatively simple setup, but then again, it is used for typically used for solid samples. Although if you have appropriate setup, you can also use it for liquid sample as well. So this is basically the setup. You have a standard material. Okay, so this is again a cross-section of cross-sectional view of the setup. And this setup is typically, it can be Cartesian. That means this material can be either cylindrical or it can be even like a cuboid. Okay, so you have a reference material, could be a metal, could be aluminum, could be steel, could be copper, whose thermal conductivity is already known. Okay, you know the thermal conductivity. Okay, and then you have a block of another material whose thermal conductivity you do not know and you want to measure. Okay, so you put these two materials one by one, okay, vertically, and all around you insulate. Okay, you can use cotton wool and very low thermal conductivity material to wrap it up. And this basically allows that the heat from the hot end to cold end goes only in one direction, okay, in this direction. So this is the hot end. You can mount a heater, okay. And the cold end is basically either exposed to ambient or you put it in a water bath or whatever, right? So you take temperature measurements at 4 different locations, 2 locations inside the standard reference material. You basically drill holes and at these 2 locations, and you know precisely the location, the distance between the thermocouple junctions, that is LA. You do the same thing in the material B, which is unknown material, and you make 2 junctions, and you should know the distance between the junction LB. Okay. So you are basically measuring the temperature difference across these 2 points and that are separated by LA. And you are also measuring temperature difference between these 2 points that are separated by LB, right? Then you apply the 1D heat Fourier law of heat conduction, which says that thermal conductivity in material A into the temperature gradient in material A, that is the temperature difference between these 2 points divided by the distance between the points, will be equal to, because whatever heat comes through the material A, same heat leaves through the material B to the cold end from the hot end, because the all around it is insulated, right? So the thermal conductivity of the material B in that case will be thermal conductivity of material A into the length of material B divided by length of material A into the temperature difference between these 2 points in material A divided by the temperature difference between these 2 points in material B. Okay. Now, this is the unknown thermal conductivity that you want to measure. So what you need to know is the thermal conductivity of this known material, the distance here, LA, LB, and the temperature difference. So all these you know. So you will be able to determine the unknown material thermal conductivity. Now, so this is the last method that we will talk about in thermal conductivity measurement. So typically here you use a transient method, and here you have the setup which is shown here. Okay, the sample whose thermal conductivity you want to measure is typically brought in the form of a very thin sheet, okay, small sheet, and the sample is kept at a fixed temperature. Okay, so you can put it inside a furnace kind of environment whose temperature can be controlled at TF. Okay, and then you are measuring, of course, the temperature using a thermocouple, and you are recording here. So initially it is at some temperature TF. Okay. Now the front end of the material is exposed to a beam of laser. Okay. And this laser or some flash would instantly applies a pulse of heat onto the front surface, this surface. Okay. And you are consequently measuring the temperature change that happens at the back surface. Because when you shine laser, you'll get heated up. So the heat will get transferred, temperature here will rise up, temperature at the back end will rise up, and which you are trying to measure. So this the thermal pulse or the laser light is supplied only over a short time. Okay, and this the temperature at the backside would rise up to that maximum temperature over a finite time, right? Because you apply some heat, but instantly it will not reach the equilibrium, the maximum temperature because of the heating effect. It is going to take some time. Okay, and this time that it takes to reach the maximum temperature because of the heating effect is dictated by what is called the non-dimensional time, which is represented by Fourier number. So this Fourier number is expressed as alpha T over delta square. So alpha is basically the thermal diffusivity. T is basically the time it takes to reach the maximum temperature from the time instant when the laser is excited. And delta is basically the thickness of the sample. Okay. So you can also define a non-dimensional temperature, which is T by T max, because T would go from initial TF to final some T max, okay, because of the laser heating. Now, if you plot non-dimensional temperature with non-dimensional time, this is the characteristic it actually takes. This is characteristics of a first order thermal system where the temperature would slowly rise and finally reach T max. Okay, it will go from TF to T max, temperature of the furnace to T max. So during this time, if you say, what is the non-dimensional time at which T is half T max? Okay, when the temperature reaches half the maximum temperature. When the temperature reaches half the maximum temperature from first order system, you can calculate using the formula that we have derived when we talked about thermocouple. It happens to be about 1.37. Okay, this is the non-dimensional time at which the non-dimensional temperature is going to be 0.5. So this 1.37 is basically your non-dimensional time. That means the Fourier number. So from this, alpha is going to be 1.37 times this delta, or call it a characteristic thickness or length scale square, divided by T half. T half is the time at which T becomes T max by 2. Now, this alpha, thermal diffusivity, by definition is thermal conductivity by density into specific heat. So thermal conductivity can be density into specific heat times alpha, which is 1.37 into density specific heat times the thickness square divided by the time at which half the maximum temperature is reached. Okay, so this is something that you can measure if you are measuring constantly recording the temperature. L you will already know. If you know the density of the material, specific heat of the material, in this method, using this method, you can measure thermal conductivity. Okay. Right. So I now change gear. So we have been talking about thermal conductivity measurement. Now we'll be talking about measurement of stagnation temperature. We had talked about measurement of temperature, right? We talked about thermocouple, we talked about RTDs, we talked about thermistors, and then we talked about the air thermometry, pyrometry, many things we discussed for measurement of temperature. Now, what is stagnation temperature? Stagnation temperature is when there is a hot fluid which is moving. Okay, if the hot fluid is stationary, you measure its temperature. But when hot fluid is moving, measurement of temperature becomes difficult using a probe, because at the probe, the fluid comes to rest because of the no-slip boundary condition. So the entire kinetic energy that is there in the flow gets converted into thermal energy. So basically, the temperature that you measure in case of a moving fluid is basically the stagnation temperature, not the static temperature. Okay. So stagnation temperature is always greater than the static temperature, because in addition to the thermal energy, kinetic energy of the flow is also converted into the heat energy, right? Thermal energy. So, I mean, equivalent to you have static pressure and stagnation pressure, like that. You have static temperature and stagnation temperature. Okay. But to measure stagnation temperature, you have to ensure that there is adiabatic condition. That means whatever the probe is measuring, it is actually measuring the stagnation temperature and no heat is being lost. Once the kinetic energy is converted into thermal energy. Okay. So typically, this is a stagnation temperature probe. So you have like a thermocouple junction here. You typically use R-type thermocouple because we have studied that R-type thermocouple has can measure up to very high temperature. So you use typically R-type thermocouple in stagnation temperature measurement. So you have a flow, and then you want to measure stagnation temperature. So this probe has got a radiation shield. Okay, that means when the flow enters this radiation shield and coming to stagnation at this probe, there is a sharp temperature rise. So there is no radiation that is happening because you have a shield here, right? So to avoid any radiation heat loss, the radiation shield is kept. So after the flow comes to rest here, the remaining fluid can escape through these vent holes. Okay. So this is a typical stagnation temperature probe, how it looks. Okay. Now we talk about this shielded thermocouple probe. So here, this probe is basically shown like this, and this is the thermocouple junction. And the fluid streamlines come and end here. This is the stagnation temperature. The remaining fluid basically escapes through these holes. So this is where you are supposed to measure the stagnation temperature. Okay. So, but what happens is there are three types of losses that can still happen. There may be conduction of some of the heat into the lead wire. Okay. So that makes the process non-adiabatic. However, radiation shield that you try to put it, and there may be some radiation heat loss that may happen. And the third type that loss that may come is that the entire kinetic energy may not be converted into the internal energy. Some of them may get lost in terms of due to viscosity. Okay. So these losses, because of these losses, the stagnation temperature differs from the actual temperature that you measure. So actual temperature that you measure is Tj, and stagnation temperature should have been more than that, should have been higher than that. So you define a parameter called recovery factor to quantify how much of this energy of the fluid is converted into the stagnation temperature. So this is T of the actual thermocouple junction temperature minus the ambient temperature divided by the actual stagnation temperature that should have been minus the ambient temperature. This is called the recovery factor. Right. So this is again a dual thin film stagnation temperature measuring device. So here, this is again the body of the probe, and these are connecting leads which are connected to the Houston bridge for temperature measurement. And at the ends, you have the thin film heaters. Okay. Now, what you do is basically these thin film heaters are heated. Okay. Heated by supplying electrical energy, let's say. So the heat that comes onto the first thin film heater is eventually gets a temperature which is T1, and the temperature of the second thin film heater is T2. Now, when you have flow, the entire kinetic energy of the flow, the enthalpy of the flow is converted into thermal energy. That means here, there is some heat transfer that happens between the stagnation point and the film itself, right? So that heat transfer is given as H into surface area times the stagnation temperature minus the temperature of the first thin film meter. Similarly, there is some heat transfer that takes place to the second thin film heater from the stagnation point, H into S2 into Tt minus T2. Now, if you try to eliminate the heat transfer coefficient, because that is very difficult to measure, if you eliminate H, you can actually write the stagnation temperature is T1 plus Q1 over S1 into T2 minus T1 divided by Q1 over S1 minus Q2 over S2. So you can see that if you have this kind of arrangement and you know how much heat you are supplying to the first thin film meter, how much heat you are supplying to the second thin film meter, what is the temperature of the first thin film meter, what is the temperature of the second thin film meter, what is the surface area of the first thin film meter, second thin film meter, you should be able to measure the stagnation temperature. Okay. So this is how basically stagnation temperature is measured. The last thing that we are going to discuss is measurement of bulk mean temperature. Okay. So typically the test trick that is used to measure bulk mean temperature looks like this. So you have air that is hot air coming, okay, entering this wind tunnel. And we want to measure the bulk mean temperature of this air. Okay, that is the objective. So initially, you have typically a bell mouth entry through which air comes in. And any turbulence in the air is basically taken care of by using the flow straightener, which makes sure that the flow becomes perfectly unidirectional and preferably laminar. And then you have kind of a heat exchanger here, okay, where these are like heat exchanger coils or tubes that you can call it. You have coolant in and the coolant out. And you are measuring the temperature of air before the heat exchanger at station 3 and after the heat exchanger at station 5. Okay. And this is basically the heat exchanger. And you have a pitot static tube that will measure the velocity of the air that is going in. You can actually move it across this duct to measure velocity at different points. Okay. And this is basically the settling chamber, and this is the fan. So basically, this fan is sucking in air and throwing into the lab. Okay. So how do we measure the bulk mean temperature? First of all, what do we mean by bulk mean temperature? So let's say this is the tube through which we have some hot fluid that is flowing. And this is the cross-section. It's a circular cross-section tube. The velocity profile is typically parabolic, 0 at the walls and maximum at the center of the tube. The temperature profile is basically inverted. Okay. And if it is a hot fluid, temperature will be higher at the middle and it will be cooler at the walls. If the tube is heated, the temperature will be higher at the walls and lower at the middle. Okay, so the temperature profile and the velocity profile look inverted. Now, you can see the total enthalpy of the flow. Okay, what is the total heat energy that is contained in the flow? The temperature varies across the radius of this circular tube. The velocity also varies as VR, temperature varies as TR. So the total enthalpy of the flow is basically calculated by taking a small elemental cross-section of thickness dr. That means the area of this element will be 2 pi r into dr. 2 pi r into dr into the velocity times density gives you the mass flow rate. Mass flow rate m into the specific heat C into the temperature gives you the total heat energy contained in the fluid, and that integrated from 0 to R. So this is the total heat energy contained in the fluid or the total enthalpy of the fluid. Okay, this is the rate at which enthalpy flows through the tube. If you divide this term, the total enthalpy across the tube, with the mass flux is basically again area of cross section times density into velocity, integration from 0 to R. If you divide this with the mass flow flux times specific heat, that gives you the bulk mean temperature. Okay, so bulk mean temperature is the total energy that is flowing across a section of the tube divided by the mass flow into specific heat. So you can see that here your 2 pi get cancelled, r gets cancelled, and only 2 pi will get cancelled. R will not get cancelled because R is getting integrated. So you have rho C will also get cancelled. So you have TR, VR, RDR 0 to R, and VR, RDR 0 to R. So this is basically the bulk mean temperature. So this is the mathematical representation of bulk mean temperature. What is the physical meaning of bulk mean temperature? Bulk mean temperature is also known as mixing cup temperature. That means the liquid is flowing, the fluid is flowing through the tube. Let's say at any instant, you collect certain amount of fluid that is present over a specific volume or specific at a particular section of a tube. If you collect all the fluid that is present at a particular section and put it in a cup and mix it thoroughly, what is the equilibrium temperature of that amount of fluid? That is known as bulk mean temperature. Because the temperature is varying across, because the velocity is varying across, you need to have a standard way of telling what is the sort of an average temperature of the fluid at a section. And that is basically represented as the bulk mean temperature or the mixing cup temperature, which is here. It is in a way represents how hot the fluid is at different sections. Okay. So that is why we are interested in bulk mean temperature, how much heat is contained in the fluid. So mathematically, this is the representation. Now, in order to evaluate these integrals, you need to know how temperature varies with R or how velocity varies with R. But instead of integral, you can do a summation by taking different, small rings and then taking a sum. As you know, integration is basically a summation where the increment is infinitely small. When the increment becomes finite, instead of integrating, you write summation, right? So a more practical way of measuring bulk mean temperature, let's say inside a tube, is by dividing this tube into a finite number of equal areas. Okay, so you can say that these are, in this particular case, you divide the tube into 10 different equal areas. So this is one area, this is the second area, the third area, all these areas are equal. Okay, and these equal areas will be represented by some radius of the center of each of these areas to the radius of the outer circle. So the first one, this radius divided by the outer radius is 0.316. In the second case, this radius divided by the outer radius will be 0.447, and so on and so forth, right? So this is listed here. So what you need to do is basically measure temperature of this area, maybe somewhere here. Temperature of this area maybe at the middle point here, there, at this point here, here. So you're basically measuring temperature of each one of these segments, basically T for a particular R. Similarly, you also need to measure velocity here, velocity here, velocity here, and so on. So you need VR, and you do a summation. Instead of an integration, you do a summation because you know temperature at different R, velocity at different R. So you can practically find out and the bulk mean temperature. Not necessarily it has to be a circular tube. It may be a tube of rectangular cross section also. In that case, you divide the entire area into grids. Okay, so this dotted line is dividing this entire area into, so here you have 1, 2, 3, 4, 5, 6. Here 1, 2, 3, 4, 1, 2, 3, 4, 5. So you have 30 smaller equal areas, and each dotted area is basically a control volume, and you measure temperature and velocity at the centroid of each of these areas. So these dotted points are basically at the points where you measure velocity and temperature. So you have a thermocouple rake to measure, temperature at all these 5 points at once. You can have 5 thermocouples here, and you move here, and you measure temperature at all these points. Similarly, you can use a pitot tube to measure velocities at all these points. So you can find out first the mean velocity by going to each one of these centroids, which are represented at V I comma j. For this, you say V11. If you go here, this is V21, V31, and if you go here, V1, 2, and so on and so forth. Here you come as V5, 5. So you measure the velocities at all these centroid points and divide by the number of elements. So in this case, it is 6 into 5. So that will give you the mean velocity over the entire cross section. Then you can find out the bulk mean temperature by, again, taking sum of velocity at Vij, then temperature Tij, divided by the total number of control volumes, 6 into 5 into the bulk mean velocity that you have found here. Okay, that gives you the bulk mean temperature. Okay. So yeah, we have come to an end with that. Let me stop this.
Recording stopped.
If you have any question, then be happy to.
So this bulk mean temperature,
Yeah.
we usually associate with some heat exchangers and pin fin or something like that analysis
Yes,
of
yes. So you are
pin analysis.
basically talking about an average information that you try to get when there is a variation in the temperature of the fluid coming from the variation in the velocity of the fluid. Okay. So this bulk mean temperature will have applications in, as you said rightly, heat exchangers and in practical thermal fluid circuits.
So it's similar to like BAP, right, sir? Like the max and mean pressure is converted to a single pressure line, and we're supposed to do same volume of work, right, sir? In that way.
You are basically getting an information both considering the enthalpy, of the basically considering the enthalpy of the flow, which is related to not only the temperature but also the velocity information.
Okay.
Can you please share like some applications, sir, related to the stagnation, temperature, and static? I think normal fluids like that we measure will be like under the static temperature, right? But stagnation, like can we consider like air means fins on the airplanes and
See, the thing is, when you measure temperature of a fluid, you may think that it is static temperature, but it is actually stagnation temperature. So what you measure will be stagnation temperature. You need to subtract the enthalpy, the kinetic energy component from it to get the static temperature. Okay. So from the stagnation temperature, you need to take out the contribution that is coming from the velocity of the fluid. Okay, so that will come from thermodynamics, where your temperature T stagnation will be some T static plus the kinetic energy component of the heat that is coming. Okay, so in order to know the static temperature configuration, what you measure in a fluid, you cannot ask fluid to become stationary and measure static temperature, right? You have to measure stagnation temperature, but then how do you get the static temperature information, right? So that's why from the stagnation temperature, you have to deduce static temperature by knowing the kinetic energy information. So now how do we measure the stagnation temperature is basically these tools are available, right? Which we just talked about.
So just for clarification, can you just define stagnation, temperature, and pressure once?
See, we talked about stagnation pressure, right? So where we talked about the stagnation pressure is static pressure plus the dynamic pressure, right? Similarly, when you talk about the stagnation temperature here, I think we do not have an expression here. Yeah. So here, for example, see, this is the stagnation temperature. Okay. And the stagnation temperature is a consequence of the not only the thermal energy that is contained in the flow, but also at what rate the fluid is flowing. So that is where the heat transfer coefficient is coming. Okay. So the stagnation, like your stagnation pressure, you have static pressure and the dynamic pressure. Like that, the stagnation temperature will have a static temperature component and the dynamic temperature component. Okay. So the dynamic temperature component is coming from the enthalpy of the flowing fluid. Okay. So if you can measure the stagnation temperature, you can predict the static component of the temperature. So that is the idea. And they are related through the thermodynamic relation. I do not have the relation here, but you can refer textbook and find out how the, similar to the stagnation and static temperature configuration, how the stagnation temperature and static temperature are related.
Noted, sir. Okay, thank you.
Sir, one request that I had made earlier that since this covers a lot of basic things.
Yes, I have not forgotten. I have not forgotten that. So, I mean, we have come to an end of the course in terms of the syllabus, but we have how many classes now? We have quite a few classes, I guess. Let me see. I think. So today is 5th. So we have one class this week and three. So I would not take class on that last week. I would give you an opportunity to prepare because
Yes, sir.
30th November is the exam. So I
Yes, sir.
would basically have 7 classes from now on. Okay. So I would maybe tomorrow or next week, one of the classes or 1 or 2 classes that I can take to clarify your basic understanding of different things that I have covered. Okay. And the remaining classes I will utilize to actually solve some questions in the class so that, you are getting some practice. Okay.
And the final exam will be like numerical based only, sir, if I'm not wrong, right?
I mean, already you have seen the midsem, right?
Right.
So it will be of similar kind.
Can we bring is it open notes or open books, sir? Open, yeah.
See, I said it is your notebook, whatever you have taken, and could be the printout of the slides that I share. But no book. Books are not allowed.
Okay, sir. Okay, yeah. Thank you.
Okay, and please do not write anything on the, these printed slides and so on.
So just to be on the same page, what you said is the last class would be on 20th, correct? That would be the last class.
Yeah, I would not take the class on the week after. I would give you time to prepare.
Right, sir.
Not at 5th. And sir, the midsem marks you have shared to the code office and we will
Yes,
upload.
I have shared the marks. I have shared the corrected answer scripts, everything. I think they
Okay.
should find a way to share it with you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Okay, so thank you all, and we'll again meet tomorrow.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir. Thank you, sir.